Hello guys, and welcome to the part 2 of building a text to SQL agent in LangGraph. Today we will follow through on our implementation. So let's start. Okay, so first of all, what we need to set up is a database, most probably a relational database. Uh, Also before that, you need to install and run Olama, and it's pretty simple to run. You can see it here. For Windows and for Linux it's available. Olama lets you run models locally. Also, you should just press Control plus Shift plus Escape to see if you have the GPU. Like here I have NVIDIA GPU with 8 GB dedicated, or RAM, because some models may not fit, so you need to be aware of that. Okay, so we first need to set up a relational database. So for that we choose Docker, because Docker is easier to set up. So this is the command for pulling the Docker image, starting a Postgres database, and this is just artificial database that we have constructed here. So you can set up RDB as, I mean, it's your choice basically. Okay. Once we have set up our database, we can proceed with the implementation. So first things first, we will set up the logging. We in this case we will be logging in NL2SQL.log file. We will not be using print statements, because again print statements are bad. Okay. Okay, so we have set it. Also, why did I load environment variables? Well, because there is a thing called langsmith, and when you are working with langgraphs you will most probably be using it. So I'll just show you quickly what is langsmith. So here I can trace my projects. So if I click on new project, here you can see you have to first generate an API key, then you have to install the dependencies, and then you have to configure your environment. I configured my environment using a .env file. Here it is like this. So you have to fill these via langsmith only. Okay, then we load our .env file, and this is just for testing, it's nothing new. Okay, so we start the graph agent. Okay, first things first, we have to load our models. Like in this case we will be choosing Qwen 2.5 coder 7b. Why we will be choosing Qwen 2.5? Because of its higher performance on tasks. As we can see Qwen 2.5 coder, even here you can see 7b on Spider. Spider is our eval on Spider and Bird SQL for SQL generation task, and 7b is performing very great, 83.1, right? It's on par with many models like GPT. So we will be using Qwen 2.5 coder 7b also, because it fits our inner RAM. The keep alive parameter is used for, like if we just do a simple, I'll show you. Okay, see, they run forever. If you don't set this parameter, they will at most run for 5 minutes. Okay. Okay, so we load both our models. This will be our main model, the brain, and this chat model is also a judge model. I have chosen both to be the same model due to memory constraint. Okay, so in that case we will be using Llama 3.1 8 billion parameter model. Okay, simply because it's fine-tuned for chat experiences, while the Qwen 2.5 coder model excels in logical problem solving and coding. Okay, then we will initialize our embedding model. For embedding model, the undisputed goat nomic, we will be using nomic for it. You can find all these models like in Olama too. Like if in Olama you go in models, you have to just sign up. Okay, so net slow hai. Okay, you can see that if you tap at embeddings, the nomic embedding is on second. I didn't choose gamma embedding because let's just say I do not have good experience with it. Okay, and if you choose cloud models, you can also interact with cloud models. There is no necessity that you have to choose embedding models only. In thinking models, GPT OSS is the absolute goat, but it's a 20 billion parameter model at least. So I've downloaded it, but it's heavy, so the inference is slow. Okay, so we load both our models. Okay, this is just for testing purposes, both of these. Okay, we use invoke whenever, because all these things are runnables. We call them runnables, and runnables have some specific methods like invoke, batch, stream. More on that on, you must have read LangChain, so you would have known this stuff. Okay, this is the important part. These are just the libraries. The typing library is used for declaring type diffs, type hints or return hints. Okay, this is an accumulator, like I will tell you about this. Okay, this is the base message class. All the messages like human message, assistant messages, they all inherit from it. This is used for initiating a instance of the SQL database. Okay, it makes our headache go away basically. You will see. Okay, this is the vector store, and this is a JSON library. Okay, so we start with the state. So before we proceed, there is one thing I'd like you to know. See, in LangGraph, the main thing is the state. The state gets passed around the nodes. Okay, the state carries all the variables you wanted to store. Like here also, you will see the state graph carries all of it. Okay, and this is the reducer I was talking about, the add messages, the accumulator I was talking about. So you can read probably from this the LangGraph documentation. Okay, but I'll try. So what do we need? We need our database information. The DB dialect is, what is the database type? The Postgres database, it's a MySQL database. Okay, this is the DB instance. As I said, the SQL database is, a LangChain abstraction which helps us to interact with databases. Okay, metadata is not used in my current implementation. I'm planning to use it, but if you happen to be around this project, you can probably add it. Okay, so we have the table vector store. I will come on it. This is used in a later implementation. Okay, pay attention. The optional parameters are used when you don't know their values at the start. They are by default initialized to null. Okay, in advanced implementation, you can use a pydantic model or a data class, but I prefer type only. This is the hash query I talked about in the architecture video, which is used in the query enhancement for if the query is worth it or not. Okay, this is our original query, whatever the user provide initially. This is our enhanced query. Okay, the message is used for storing conversation history. Okay, so we can even write that here. Okay, so conversation history is stored here. Okay, in the table discovery state, see, these are all, I have commented them in order of the nodes. Like the conversation node required this, the embedding node required this. So the table discovery node wants two things: the number of tables available in the database and the metadata of each of the tables. More on metadata later. I will tell you in the you know query generation node. Okay, these are the schema nodes, like the top k relevant tables we were selecting. So we select the top k tables and each of their schemas. Okay, these are the name of the table and these are the schemas of the table. Okay, then from the query generation node we store the generated query, explanation of the generated query, and the confidence score of the query from 1 to 5. Actually the confidence score is between 0 to 1. Okay, it can be any real number between 0 to 1. Okay, the critic node is the reflection node. It gives out a suggestion, like I talked in the architecture video also. A suggestion is passed from the reflection node to the generation node. Okay, these are the execution result, whatever the SQL query returned. Execution status: pass if it ran without error, and fail if it caused an error. And this is the exact error. Okay, these are hyperparameters we can tune, like the similarity L2 threshold. The L2 threshold is for vector similarity. Like in the architecture video, I said the cosine similarity, but the phi store uses an L2 threshold. It's inverse, like if cosine similarity is low, it means they are not similar. But in L2 threshold, if the distance is low, it means two vectors are similar. Okay. Also, this is the confidence threshold. This decides whether the reflection node will be triggered or not, and the SQL limit top k limits the SQL query results to whatever we choose, like top 5 results or top 10 result. And this is used, generation critique, loop count, and max retries are used so that the generation loop and the reflection loop don't get stuck in an infinite loop. Okay, it sounded like a tongue twister. Anyways, and this is the final model answer. like the very final model answer as I told in the architecture videos first 3 minutes. Okay, so let's start with this. I'll come on this in a moment. These are structured output models. I'll just, okay, wait, I'll first show you the relevant things. I've just structured it in a way it's visible. Okay, let's start from here. I'll cover the above things uh, with the flow. So we talked about how we would use the R3 approach for writing and reading the prompts, like transforming it, enhancing it. So how would we do it? Okay, the state messages is the messages object. It carries the conversation history, and by -1 we know that we have to get the last message, whatever the user typed last. It is the main user query that we have. Okay, the prompt is prompt template query and answer dot invoke, and the messages is the conversation history, and the original message is user query. The I will tell you the prompt template is, like I told you, it's a fancy prompt engineering technique. See, this is the prompt for a SQL enhancer, and pay attention to the prompt funnel because prompts are very useful in this application. See, you are a SQL prompt enhancer. We use role play with models because it's proven that role play, like telling the model it is specific. Like if would have used this model for designing a website, I would probably have used you are an expert website designer. But we are here giving it a role play of you are a SQL prompt enhancer. Okay. Extract the database question from conversational text and enhance it for SQL generation. Please keep in mind it's not your job to make a SQL query, but rather enhance it. This part was added rather by me because when I was experimenting it with it yesterday, it was continuously generating an SQL query because the models, the smaller models are aloof and they may, they see you are a SQL. In fact, I didn't write prompt here too. I write it you are a SQL enhancer only. So yes, some English classes are in order. Okay, so this is the user message. See, this is like an f string, like we do in f strings, right? We write f and we use these curly braces to fill out the variables. Okay, okay, so original message is passed here, whatever the user's original query was. Okay, these are the tasks. See, these should be explicit whenever we are giving a prompt. And I'll be honest, this prompt I just gave a template to Claude and he generated this prompt because such a beautiful and clean English is difficult for a human to generate. But anyways, so tasks is ignore, extract, enhance. I think you can read all of this. There is no need to go through it, but I'll tell you one thing. See these examples. These are few shot. If you don't provide an example, this is a zero shot prompting. But if you provide a few examples, this is a few shot prompting technique. Okay. Like if we give input hi there, can you show me recent sales by regions? Thanks. Show total sales. So see, he didn't reply to hi there because the relevant part was only can you show me recent sales by region. So it automatically inferred that show total sales amount for last 30 groups by region. Okay, these are the rules and these are our rules. So in prompt template what we do is, seen this, first is the system prompt. Whatever we just discussed was a system prompt. It will be passed in no matter what, and then comes our all the conversation history. So this will be part of our message history whether we like it or not, and that is what we want exactly. Okay, uh, so where were we? Okay, so we have a prompt, okay, with the original user query. Then what we do is chat model. See, chat model was our original Qwen2b model, if you remember. Sorry, the llama model, in fact. With structured output, what does it do is, see, R3 is a pydantic model. Here it is. It inherits the base model is a pydantic base class. See, here it is, as you can see. Okay, so what this base model does is it provides a structured output of a retriever read write pipeline for prompt enhancement. What it means is the model, whatever the output the model will give, it will adhere to this structure. If I add, another variable and make it a stir type, the model will output this also. Okay, and whatever the description we provide here and the doc string we provide here, it is used by the model to fill out these variables. Okay, so as I said, this is the enhanced query, and the has query variable is whether the current query is worth processing or not. You can read about it when you read the LangGraph documentation, how structured output works. So you can also use a type dict here, not if you don't want to use a base model, and it's totally up to you. Okay, so where were we? The pydantic model forces a structured output, so we use a small model with structured output model. we invoke it with the prompt and we gather a response. Okay, this is just a logging part. Just I did it for debugging. You can probably remove it too. Okay, now see, in nodes, this was all a node. In LangGraph, whatever Python function which takes a state object is called a node. Okay, and it always returns a dictionary. In the dictionary, it only updates the state. Whatever variables of the state are updated, it will only return. Like in the state, we had user query, so it updated user query by resp of enhanced query. Yani whatever the query was, it will be replaced by the enhanced query which was generated by our R3 model. Okay, and whatever the you know response we got from the hash query, whether it was true or false, we stored it in the hash query variable. This will be used to further direct our graph. Okay, and see, this is the query routing function. It is part of adding conditional edges. When we connect the nodes, you will know why I declared the function this way, whether it returns just true or false. So okay, now this is the table discovery node. Again, it takes a state object and it returns a dict, so we can safely say it's a node. Okay, but it does it uh, it loads a DB instance. Now this get usable table names is a SQL instance method. If I hover over it, you'll get to know it. Where was it? Where was it? Where was it? Of this. Okay, it's an SQL alchemy method. It's a very popular method. What the SQL database does is it wraps your database in an instance, it loads the useful variable, and the get usable table names is only returns the name of the tables you have in your database. Okay, if there were multiple databases and I switch this DB instance, it will give the table names of the database, whatever number the table names are. Okay, then I log it and I return whatever the available tables have been found. Okay, so that is the table discovery node. We have made it traceable, so Langsmith can trace in. More on that later, I will convey it. Okay, next thing. Now this is how we select the tables in the schema. Okay, again it takes a state and returns a dict. Okay, again we select the user query as the same way, we log it. Now see the vector store. The vector store is initialized below in the bottom half of the program. Okay, so in the vector store we perform a similarity search. Now how this similarity search is, if you probably hover over it, you will know. It returns a list of tuples, doc and similarity score. See, the similarity searches always happen between the document object, and document object in LangChain, you will know, contains of content and metadata, two things. Okay, so this results contain a document object and a score. Okay, now this is a fancy Python way of list comprehension. I could have wrote a for loop, so this is a very Pythonic way to write it. Okay, so I can go on and on about what this code does. I can probably explain it, but due to time constraints, just understand that it extracts the most relevant top case schemas of the tables that are relevant to us. Okay, also pay attention to this condition here. See this one, in fact this pure, what it does is it iterates for each of the table. Okay, and if it finds that a most similar table with score table is less than equal to state similarity L2 threshold, the similarity L2 threshold will be set by us when we initiate the graph. Okay, what it says essentially is, if we find that any of the okay, so this is the most important part. See, the doc strings are necessary. In here I did not give a doc string, so I'll probably give it selects the most relevant queries. Okay, schemas, sorry, not queries. Now the query generation node, this is the main brain we use for generating SQL. Okay, like in the architecture also I told you, this communicates with the execute query node and the reflection node. Okay, so for it we provided a prompt. See, the time is not enough, so I'll probably hurry it up. You can check out the code for what the prompt is. Okay, we again use a SQL generation structured output. See, the SQL generation structured output is again a pydantic model. It has three things. Okay, the SQL query, okay, which is a syntactically correct SQL query, an explanation of that query, and a query score. And I provided few short examples of what those prompts description code should be. If it's completely irrelevant, you generate 0 to 0.2. GA and LE are upper limits and lower limits. Okay, it's a pydantic way of enforcing the outputs. Okay, so where were we? Okay, then. Okay, so we get a structured response. We store our confidence score, SQL query, and query explanation in separate variables, and we return them. Okay, we could have directly returned it, but being verbose helps when you don't know what you're writing unless you are using Claude, which I don't like much. Anyways, so okay, so this was the route. Again, this is used for adding conditional edges. Like the earlier also we talked about, another routing function. This is another routing function. Okay, if I'll show you the graph, you'll understand. Okay, this is the reflection node. What its job is to criticize whatever output it got and give suggestions to the generation node. So the generation node can act upon it and improve its just equal generation quality. Okay. So also see, pay attention here. The retries count update themselves. See, you can't just do that. You update the state in place. In fact, updating the state is not permissible. It leads to, because internally the lang graph is converted into a quantized version and it messes up with its structure. So it's always that you update and return it with a dict. Never do like this, like state square bracket single colon return retries count plus equal to 1. That will mess up the quantization. So pay attention, because I did it and it introduced a bug. So yes. Okay, this is the execute query part. Yeah, I think most of this code is self-explanatory in way. The format, this is a very useless code I wrote. In fact, this is just for debugging purposes, so you can ignore it. Okay. Now let's come to the final LLM node. See the final LLM node. I'll tell you what is final LLM node before I show the graph to you. See, this is the graph. I'll open it here. Okay, we start on the upper node. Okay, we r3 prompt enhancement, but I told you in the architecture video too, the prompt is enhanced. Okay, if we think that the prompt is not relevant, if it falls, we directly conclude to the final LLM call. The final LLM call answers based on the query only. It's like a simple chatbot. But if we think that it is linked to a database question, okay, then we first discover whatever tables are in the database. We also collect their schemas, then we select the relevant tables and schemas based on their embedding scores, like we discussed in the architecture video. After we have the most relevant, we provide it in the prompt in the generation node. In the prompt we have three things: the message history, our system prompt, and whatever the relevant schemas information we got. Okay, then we think that if the confidence score is low, okay, we rotate to reflection node, and the reflection node rotate back to generation node, and it happens up to n times. The graph didn't show it n times because it is not programmed so, but it happens n times until either the confidence score passes a threshold or max retry is complete. Okay, once we have the confidence score, the generation node goes to execute node. The execute node formats, the format is simply pretty printing. In fact, you can ignore that this exists also. Okay, and then the final LLM call with the relevant query explanation and the original prompt. The final LLM call is made and the graph is ended. Also, you can uh, do a simple rotation that if execute node fails, you can simply switch back to generation node also. Okay, and that's entirely up to you. But because the time was low and the latency could have been increased, I simply got around it. Okay, so we have the reflection node, we have the execute query. Okay, format results is done. Okay, see the final result, final LLM system prompt is: you are a knowledgeable healthcare assistant. You can probably invoke this also if you think that the database can be of healthcare or cannot be of healthcare. You can probably invoke this and make it something else. Okay, you are a knowledgeable health assistant. Your role is to provide helpful, accurate information about general health topics, medical condition, treatment value. So we give it the question, whatever question here. The question means original query by the user, the SQL query, and the results, whatever the result we got. Okay, then we provide a natural language results and empty state that no matching was found. This last line is for if the r3 query and answer directly directs us to the in the graph also we saw now. If the prompt enhancement directly gives us false, then these queries and discover tables are never discovered. So remember, we used optional in the front. Like if you go here, we used optional here. The optional comes in handy now, because if you wouldn't have made it optional, you have to initialize the dictionary keys, but optional initializes them to null. So automatically what happens is, I'll show you here, these all values are set to null. Okay, and we say if the results are empty, or null, Okay, state that no matching data was found. So it covers both our approaches. Okay. Okay, so the prompt template finally is just a simple system prompt. It never changes. It's a simple chatbot call, stateless. In fact, no conversation memory is needed here because it is handled automatically by the R3 query prompt and answer. Okay, okay, we make it traceable. Okay, the cheese the prompt will be invoked by enhancing it, invoking it. Okay, then the final model answer is updated. Pay attention, the final model answer is a state variable. Okay, and we updated with the final answer whatever content we got from the jack model invoking the prompt we just defined in the system. Okay, so now see, this may vary. I told you in the details.txt also. Making a docker container is very simple. If you search postgres database docker, you'll see a official docker page also. See this, or this one, postgres 15 is the latest version. Okay, I'll just tell you real quick how to make it. In fact, you can chat gpt also this thing. Okay, how to make a docker container. Okay, it's very simple because if you manually do it maintaining a db, as I also have less experience in maintaining db, so I thought docker is the way to go. Okay, and I have hard coded it again because I did not want to mess up my environment variables. I struggled a lot with environment, so you have to probably, for best practices, if you are uploading it to version control or elsewhere, always set them as environment variables, whatever. Okay, so see, the SQL database is an SQL Alchemy wrapper. It initializes from a URI, Uniform Resource Identifier. Okay, the PGURI. This is repetitive syntax. You can even find them in Stack Overflow pages. Okay, okay. See the table description. It is essentially a metadata. I will just write here. I see. I told you na, the tables have each of the metadata. Here I manually provided them. Metadata of the tables. Okay, because you can also provide them directly in postgres, but since I'm a postgres sql noob, I didn't know much, so these are the metadata content. Okay, like the patient table as stores patient demographic. See, this will be used by the model because it doesn't know, like, these names are explanatory. See, but we have doctor and dr r. Okay, so how do we know what is doctor and what is dr r? It would have been medical record, so metadata comes in handy while describing the tables. Okay, see, this function is used for initializing the embedding. See, in the state we used, we passed vector store. Here, see, vector store was passed. We didn't pass embeddings as is because vector store stores it in an optimized form. If we directly pass embedding, the state will be very heavy. If we have 10 tables, 100 tables, we can't just pass 100 into 100 or 100 into 768 embeddings. That would be catastrophic and slow both. Okay, so what we do is, it's a simple, see, in this whole function, if you carefully read it, what we are doing is we are simply giving a description for our embedding model to embed. Okay, like this gets the schema info in sql database. By calling get table info, you can get the schema, like how the table is contained, what are the constraints. Okay, you can manually do it, of course you can manually do it, but again that requires knowledge of sql. If you know, let me know. I'm also quite curious how it is done in langchain apart from this method. Okay, so we have a description. What a description contains is, this is a SQL database table name, whatever the table name is, and the table name we got from whatever we pass here. See, here, table descriptions. Okay, okay. Sorry, metadata is table descriptions. What we are passing in table names, I just quickly show you here. Table name. Okay. When we call db.get usable table names, it generates all the table names in a database. We iterate over each of the table name and we create a description for its relevant metadata. Okay, so table name, its metadata, whatever schema is at, and the purpose is this table contains information. This is just for the embedding model to generate better embeddings. You can probably skip it, add more to it. It's purely your choice. Uh, if you pay attention, the BERT model is used for embedding. Okay, so BERT model again is a attention based model. You can probably see it also here. Okay, see, it is a stack of encoder only model. It generates embeddings of fixed size like 768. Okay, you can learn about BERT models to understand why I provided this purpose. Okay, you can strip is just for uh, from the start of the string and from the end of the string you just have to remove spaces or tabs. Okay, this is just for building a vector store. It initializes embedding and stores them in the files. The files is a in memory, vector store. I used it because of ease. If you are working in more like a production environment, you will probably using something like Pinecone, or there are many vector databases, or something like as yours. Okay, we build a vector store. Okay, so now we have a vector store which contains the embeddings for each of the schemas of the tables with their relevant metadata. Okay, fine, quite a wrap. Okay, now this is the part. See, from here to here all we did was initialize the nodes and define them. Okay, here is where we connect the nodes. We initialize the graph with a SQL editor. It is showing a squiggly line because we used a type dict. So the lang chain will probably depreciate it. You can use a Pydantic model, but I didn't go the headache because it was working. We add a node, see whatever functions we defined here, and these are the names of those nodes: the RT prompt enhancement node, the discover table node, select table node, generation node, reflection node, execute node, final LLM call, formatting node, and whatever the functions they point to. Pay attention, don't use parentheses. These are not function calls, these are rather callbacks you are passing. Okay, we initialize a state graph. These are only nodes. See, we have not defined edges. Okay, we add edges here. Before we were before this set entry point we introduced, we probably used this start. We also imported start here. Okay, but this has been depreciated again. So we set the entry point. The set entry point will be R3 prompt enhancement. Okay, then see, we will probably use conditional edges. I told you the query routing functions. In the query routing functions, if it returns true, we will go to discover table node. The discover table node will start a chain uh, which processes the SQL, starts the reflection purpose, and if it returns false in case, we will directly output the final LLM call. This is a pretty syntax. You can check in the LangGraph docs also. I'll just show you very quickly. See this, they are given start node and see conditional node. If you want to optionally route to one or more edges or optional determinant, you can use the conditional method. Okay, you can probably do this by the routing function. Instead of returning true false, you can return the names of the nodes one. But when I was creating routing function, I didn't know what I would name the node, so I just wrote a routing function. This is the method I was talking about. You pass in the node which you want to execute, the routing function will be executed next, and based on the result, now see, these are two values, true and false. You can probably give something like 1 2 3 4. So there can be multiple branches too. Also with true you can go to two nodes also. So this is the beauty of LangGraph. You can execute multiple super steps. Right, let me just drink water. Okay, so from here we add an edge from discover table nodes, select table nodes. See, this is just connecting all the parts. Okay, as I mentioned in this graph also. Okay, so you can probably do this also here. Final LLM call and formatting node both point to the end. This is necessary because if you don't point it, it will be bad practice. Like closing a file is a good practice. You have to do this, and we have to compile the graph. Compiling, what compiling the graph does is it purges any orphan nodes, or optimizes it for running. Okay, we are just coming to the fun part. This is okay. So we initialize the graph. This is how the graph is made. Okay, you can make it more complex. See, there is a loop. If a node points to where it was pointed to, it forms a loop. Okay, so you can do it anyway. This is called the reflection node I was saying. Okay, this is a simple query. You can take it from the user, initialize a streamlit instance, but I didn't find it feasible to initialize a streamlit instance. It's such a small task, so I just made a content. Okay, this is the initial state. The initial state, listen, the whatever variables we pointed as optional, we didn't pass them. This initial state will be used for invoking the R3 query enhancement, because that is the entry point of a compiled graph, as we set here. See, set entry point. So what the R3 prompt enhancement takes is, in fact the whole graph state takes is DB dialect. Dialect means what database it is. Is it a Postgres, is it a MySQL, or maybe it's a cockroach DB, whatever. Okay, The DB instance is a SQL database instance. I told you this earlier. The vector store consists of embeddings of the tables and their schemas. The messages is the message history. The original query is this, whatever we wrote here. Okay. Is the similarity L2 threshold? I set it so high because I wanted to test it. You can set it to something like 0.8 or 0.7 to only select the relevant tables. This is the confidence threshold. If the model is less confident than 0.9, it will trigger reflection node, the reflection pattern to be more precise. This is the limit. How many SQL queries, sorry, SQL queries, how many results will be generated by the SQL query. See, if you write a SQL query, you write it like this: select star from table name. It's been time since I wrote SQL. Limit 5. Okay, so it generates only 5. So that is why, because it doesn't put unnecessary strain. You can probably do it without it. And this is the loop counter and loop retries. Like you write a while loop with I equal to 0, similar thing. Okay, it's a fancy way of writing it. Okay, now I will run this and I'll show you one thing, how the running happens flow by flow. See, with that you will probably understand. Once a minute, I should just filter it. 30 minutes, right? Okay. See, what the good point about initializing Langsmith, as I told earlier, is you will see. First, let me run above cells. See, they are running. Also, it will take 1 or 2 minutes only. Meanwhile, I can tell you one or more things. See, in Olama, there are multiple commands. You can use the list commands to list all the open source models. Okay, I've downloaded like this Gamma 2 billion model. These are the number of parameters. Okay, and each model excels in specific tasks. This coder model excels in coding. Okay, these nomic embed text excels in embedding. Okay, like this is the latest GPT open source model, the the Saltman kid. So these are all the models. You can also list out which models are running by running the ps command. See, I have ran 3 models, but Olama does is Olama runs loads one model in GPU. If the other our 2.5 coder model is also initialized, and if I call it, it will be initialized. So that is just because in GPU this model run faster, so it loads them one by one. Okay, see, it occupies 6.1 GB, and if you run NVIDIA SMI, you'll know. See, from 8 GB, only one model is occupying 5475 MB. So I think around 2.5 2.5 GB का model ही चल सकता है. Okay, so see, I'll start this and you will know. And also what these logs do is, if I start this execution, what happens is the logs are also formulated as we go. Okay, see, the logs are formulated, but I'll show you in Langsmith. Langsmith will make it clear. This would happen. Okay, see, in Langsmith it started. These 1, 2, 3, 4. These are just for testing purposes. Ignore them. Okay, this is our vector store being initialized. You can probably see it. Okay, it outputted a FICE object. Okay, and in this the main execution follows. I'll just show you real quickly what happens. See, first let me, this is the flow till now. The graph is executing one by one, but I'm just showing you. It is now in reflection node. It took time in prompt enhancement 1.48 seconds. The discovery table took 0 seconds. Select tables took 0.05. Generation took another 10 seconds, and execution took another 1 second. Okay, I'll just show you expanding. Okay, what the prompt enhancer did. The prompt enhancer received these arguments. Also, this was the original message passed by us. Find the top 3 doctors in each department who have handled the highest number of appointment. So what it did was, just a minute. See the cell execution, even cell execution finished. Okay, so what it did was is filtered this query into this: show top 3 doctors by appointment count for each department. If I could have wrote like hello, how are you, it would have filtered that also. Okay, so R3 prompt enhancement did it work. Okay, and it outputted true. If we wrote nonsense gibberish, it would have outputted false, and then we would have probably routed directly to final LLM call. Okay, so R3 prompt enhancement did it. Then comes the discover table node. Okay, discover table discovered these 9 tables. Okay, it job was only this. Now see the select table node. What it did was, select table node had a the similarity through threshold of 0.95. What it selected was two tables, appointment table and the doctor table, okay, and their relevant schemas. See, the appointment table had the schema, the create table appointment and the three rows from the appointment table, okay. This is generated automatically. Okay. Now see the generation node. This is the main brain I was talking about, okay, of the node. uh, we start with this original query, find the top three doctors, okay, the confidence threshold. I'll just show you real quickly. See the output. It generated this query, select d dot department id first name whatever this was, okay. It also outputted a query explainer. This query joins the appointment and doctor on the doctor id column if then groups, okay. So it output and it gave a confidence score of 0.9, okay. So if we pay attention here, our threshold of confidence was 0.9, so this will not go to reflection node because it is confident enough. If it would have been 0.8, reflection node would have been triggered, or I think I made a logic such that in equal to also it get triggered, we will know, okay. Okay, I'll show you real quickly. Yeah, the logic is there. If 0.9 also it get triggered, okay. So it reflects, see how it reflects. First it got the query, whatever query we generated from earlier which I showed you. The state has been updated, listen, the because of that the state is updated, the query explanation, okay. Now what it output, you can see it criticizes, it gives a suggestion. The given SQL query is generally correct but requires a minor adjustment for optimal result. The query joins the appointment doctor table based on a doctor id, okay. So it gives a suggestion. इसने ये मतलब ये suggestion है, and if the generation node wants, it can probably improve it. So we'll see if the generation node improves upon it or not, okay. See, it receives an input at the critic suggestion, whatever the suggestion critic gave, okay. It has its generated query, its original query, its query explanation and everything, okay. So what it outputted, okay, it outputted a slightly different query, okay. As you can see, it limited by 3 also, even we gave it option as 5. 1 minute, okay. And now see, now comes the final LLM call. Critic suggestion is there. The final LLM call, what it does is, I'll just show you. See, it gives a final answer, okay. So if we would have run it like this, okay, if I, in fact I have not tried this, so let's try it. There are bugs, you know. If I write total gibberish here, hello, how are you, is the weather fine, uh, can you help me with something, okay. And we initialize and then we also combine, okay. So what I want to see is whether the r3 query and answer works or not, okay. Because see, we have generated gibberish here, hello, how are you, can you help me with something. This is total gibberish, this doesn't have any relation. What we want is this aage wala part, okay. Let's see. What the prompt and answer did. See, it ignored this part, hello, how are you, can you help me with something, and it only outputted this, show top 3 doctors in each department by appointment count. And if you would have, this is the essence of what I was talking about, the prompt enhancement. So it automatically did. And even so, I'll just interrupt it real quick. So you know wait, interrupt, shut down karna do. Whatever happens first, the interrupt or this interrupt happened. If I would have given it something nonsense like this, hello, how are you, can you help me with something, are you chat GPT or llama, okay. Now this is total gibberish, it doesn't have any database question, so the r3 prompt and answer should flag it, okay. See, it even gave an answer. See how much time it, I'll just show you. See, 1.29 latency, because why, I'll just show you real quick. What the prompt enhancer did was, it gave a message, okay, it outputted no query found because this was total lameness, and has query false, and it redirected directly to the final LLM call. And you'll see why this is a good thing, because for nonsense output, if I gave a very big text also, see the latency difference, 60.99 second to 1.29 seconds, a 59-second latency saving. So the prompt enhancer was used for this. Okay, this was in Microsoft paper. If I'll just query it, rewrite, retrieve, read, this one. Okay, so you can read about it, why it works, why it's a good thing, and there are multiple strategies. So there is also a hypothetical documentation technique. So if anyone is seeing this, do refer to it. Okay, so thank you for watching it. And also one more thing I had to tell you. Where was it? Yeah, never mind. Okay, thank you for watching. And also, you can probably just look at the architecture video I shared earlier, the part 1. Okay, the architecture video explains what I just said in this video. And also remember, langsmith is your best friend. This langsmith, what I told you just now, where did it go? This one. This langsmith will help you trace, it will help analyze the latencies. Okay, so use langsmith. Okay, it can also generate a dashboard like this, whatever the trace count was. Okay, group by last 7 days, whatever the LLM count, LLM latency. In this case, we are using an open source model, but if you are using an closed source one, you will probably want to see how much tokens you are probably using. Okay, it also gives tokens. Okay, so, and thank you for watching. And please refer to the first architecture video. If you did not understand anything, I'll probably write a Medium article or a readme.md and attach the GitHub link. So, and you can also connect. So thank you for listening to me, and thank you.